Let us get some insights into the flow field in turbulent internal flow. It may be recalled that in the previous lecture, we had actually started with the log law profile for the velocity in the pipe. We argued that since the log law region in the case of a pipe appears to extend up to y plus greater than 1000 based on experimental data, we said that this log law profile is applicable all the way from the wall to the center line. So we will take a closer look at this solution in this lecture. So we start by calculating the maximum velocity in the pipe, which occurs at the center line r equal to 0. So, so we calculate the maximum velocity which occurs at r equal to 0. So if you substitute r equal to 0 in the log law profile, this is what we get. We can then combine this expression for W max with the earlier expression for W bar that we derived. So this is the expression for W bar, the average velocity that we derived earlier. So we can combine the two and then write the ratio as a function of Reynolds number or friction factor. We have chosen to write it in terms of friction factor here, but in the case of a smooth pipe, friction factor depends only on the Reynolds number. So this is the ratio of the average velocity to the maximum velocity. It may be recalled that this ratio was equal to 0.5 in the laminar case when the velocity profile was a paraboloid of revolution. In the present case, the ratio has been calculated for different values of Reynolds number starting from 4000. And it can be seen that the value is higher than the 0.5 corresponding value for the laminar case right from the beginning. And it keeps increasing as the Reynolds number increases. In fact, for Reynolds number 10 raised to 8, this ratio is 0.9, the average or maximum, which suggests that as the Reynolds number increases, the profile becomes flatter and flatter or fuller and fuller, and it begins to resemble plug flow profile as the Reynolds number increases. In fact, if we go back to this illustration, we can see that this resembles almost a plug flow profile with the velocity remaining constant for most of the cross section and then decreasing rapidly to 0 as we approach the wall. In fact, this velocity profile also reminds us of the boundary layer velocity profile that we saw earlier. So in fact, it may be recalled that boundary layer velocity profiles in the laminar case were usually written as u over u infinity, where u infinity is the maximum velocity or the free stream velocity. So u over u infinity equal to some function of y over delta, where y is the distance from the wall and delta again is the boundary layer thickness. So if we look at this profile, we can probably correlate the radius r with delta, and y, which is the distance from the wall, is actually capital R minus small r. So we may actually think of writing this velocity profile perhaps in a similar form like what we did earlier in terms of y over delta, that is u over u max as a function of y over delta. But this is what we are actually going to do next. Now, the log law velocity profile that we have is actually not in a very convenient form because the friction velocity W star appears on both sides of the equation. So it's kind of an implicit relation, not in a very convenient form. So Nicorard said, following the idea that we just mentioned, namely that u over u infinity is some function of y over delta, actually try to write the velocity profile for turbulent internal flow in the same manner. So he wrote W over W max equal to R minus R, which is similar to Y in boundary layer terminology, divided by R, which is again similar to delta in boundary layer terminology, raised to the power 1 over n. And what he did was he obtained values for n at different Reynolds numbers using a curve fit of the experimental data. And the values look like this. So for various Reynolds number, he obtained values of n. So n is around 6 at Reynolds number 4000 and then increases to about 10 or so. when the Reynolds number is about 3 million. So this form is actually very convenient, but the dependence of n on Reynolds number makes it less attractive, number one. Number two, the problem is the wall shear stress cannot be calculated using this expression. Wall shear stress is basically mu times du dy. And if we differentiate this expression, because the exponent here is fractional, if we differentiate this expression, the wall shear stress or the derivative goes to infinity when y goes to 0. So this is not in a form where we can actually differentiate and then get the wall shear stress, but it is convenient for other analysis. And the other thing that emerges from this is that it is quite clear where the profile for turbulent boundary layer, namely u over u infinity equal to y over delta raised to the 1 over 7 came from. So it's clear that the power law profile that is widely used for turbulent boundary layers, turbulent boundary layer over a flat plate, the 1/7 profile, it's clear where the profile came from. And it is valid up to Reynolds number of about 10 raised to 5 or so. Now let us look at pressure drop in laminar and turbulent pipe flows. In the case of laminar flow, the friction factor is 64 over Reynolds number. The dependence is known, so we can actually write the pressure drop in this form. So you can see that this brings out the dependence of the pressure drop on the various quantities here, on the various parameters of the problem. In the case of turbulent flow, it may be recalled that the Prandtl's universal law of friction is an implicit relationship. So it looks like this. So F appears on both sides. So there is no closed form expression for F in terms of Reynolds number in the case of turbulent internal flow. However, if we restrict the range of validity or range of application of Reynolds number, then for Reynolds number up to 10 raised to 5, Blasius gave an expression or correlation for friction factor, which looks like this. So this is in a form where F is F of Reynolds number. And if we use this correlation, then the pressure drop in the case of turbulent flow looks like this. Now we can actually make a one-on-one comparison between the pressure drop for the laminar and turbulent cases. We can see immediately that the pressure drop in the case of laminar flow does not depend on the density of the fluid at all, whereas density dependence is seen here. The second point is that the dependence of pressure drop on viscosity in the case of laminar flow is stronger than it is in the case of turbulent flow. Here the dependence is mu raised to mu itself, and here it is mu raised to 1/4 power. Now, the next important thing that we observe here is that the pressure drop in the case of laminar flow is dependent on Q, whereas in the case of turbulent flow, it is dependent on Q raised to 7/4. So it is almost proportional to Q square. And the dependence on diameter, as you can see here, in the case of laminar flow, is d raised to the power 4 inversely. It depends, pressure drop depends inversely on the diameter as d raised to the power 4. In the case of turbulent flow, the dependence on diameter is stronger, inversely proportional, but d raised to the power 4.75. So the dependence on flow rate is almost Q square in a turbulent flow compared to Q in a laminar flow. And the dependence on pressure drop is pressure drop on diameter is even stronger in turbulent flows. For instance, doubling the diameter reduces the pressure drop by a factor of 27 in a turbulent flow compared to 16 in the case of a laminar flow. So it makes sense to increase the diameter of the pipe in the case of turbulent flow to reduce the pressure drop. Of course, the drawback with this strategy is that higher flow rates would be required, number one. Number two, the weight of the pipe also increases, thereby increasing the cost. So one has to draw a balance between increasing the diameter versus increasing cost and other factors in the case of pipe flows. So that concludes our lecture on turbulent internal flows.